Mm-hmm. Yeah. Hmm. Stage directions were not obeyed. Hmm. Let's see. All right. So what observation we played around with the definition of the big intersection last time. Okay. Which maybe gave us some insight into how to solve this theorem. Which theorem? Let's see. I thought we were working on a theorem and failing to solve it. Maybe not though. Yeah, well, let's see. Well, what was the last theorem we did? No, we did. Hold on. Actually, maybe we didn't do either of these theorems. Well, there's theorem 84. Okay. Oh, I'm on the wrong page. That's why I'm confused here. No, I'm not. Alright, whatever. We'll do theorem 85. Okay. And what is theorem 85? Hold on. Yeah, get that out of there. Let's see. Let's zoom in. Alright, theorem 85 will be... There exists a D such that D is an element of B. That would be the full, yeah, okay. There exists a D such that D is an element of B, then A union the big intersection of B is equal to the big intersection of A union C, the big intersection such that C is an element of B. Whatever all that is supposed to mean. Alright. Alright, so there exists a D such that D is an element of B. Okay. Which is an indirect way of saying D is not equal to the empty set. Okay. So A union B, rather A union the big intersection of B. Rather, X is an element of, yeah. Alright. Yeah, we can go up here. X is an element of A union big intersection B. Okay, if and only if X is an element of A or X, or for all D, for all E, let's see if E is an element of B, then X is an element of E. Okay. So both of these are going to have for all X. Okay. X is an element of A, union big intersection B, if and only if for all X, X is an element of A. I don't think we need the second quantification. I don't think that adds anything. Okay. And now we're trying to get to the big intersection of A union C such that C is an element of B. Okay. Now, okay. X is an element of big intersection of A union C such that X is an element of C if and only if so this is tau, which I'm going to keep underlining with the same color we've been using. Pop it red here. This is tau. What is this tau expression though? So I say X is an element of the big intersection of tau of X. I say S is an element of the big intersection of tau of X such that X is an element of C. Okay. I'm biasing myself with that. Let's choose F. Okay. Though I wonder, might it not be useful to might it not be useful to give variable names? Actually, that would be a good argument for lean. That would be a good argument for doing all this in lean. I'm not giving lengthy variable names because there's a mismatch between just sort of injections of my cursive and sort of format of this. Whereas if I wanted lengthy variable names in lean, it wouldn't matter. If and only if x is an element of f, if and only if, or no, s is an element of the big intersection of tau of x such that x is an element of f, if and only if let's see. So this would be tau of a, but there exists a g such that there exists an x such that g is equal to tau of x, and x is an element of a. Then s is an element of g. Okay. Now the question is, how do you do that? Yeah. If and only if there exists a, and we'll just say g here. There exists a g such that there exists an a. How is that going to be x as an element of? Is that wrong? Yes, that is wrong. It's supposed to be c as an element of b. I see. So you have to figure out how to rearrange the letters, playing musical chairs with template positions here. So it's x here, there exists a c such that g is equal to a union c, and g is an element of b. Okay. Then x is an element of g. Okay. rather be C. As we can tell here. So the format here, let's do the coloring. So we have X, 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 X. Okay. We have S, and we have S. We have F. Yeah, this should be F. Okay, and then G. Okay. We have G here. G. Okay, and we have G. Okay, and then we have B. Okay. And instead of X, we have C. Okay, where tau of C is equal to A union C. Mm-hmm. Okay. Well, that all seems to be in order. Yeah, I don't know about this. No, I guess I see it. Maybe. If and only if. Hmm. Rather. Well, somehow we've gotten there much more efficaciously. No, that's not so clear because it's not clear what role this C as an element of B is supposed to be serving. Hmm. Oh, hold on. I just recalled my policy of catch and release. There's a moth that's strangely stationary over yonder. First catch and release of the season. How exciting. I'm right back. right. So this E could have been C. Presumably. C equals A union C. Oh no. Yeah, we can't line that up. For all D. D is an element of well, so there's a point here that these are all ors. So if nothing else, we can immediately take x as an element of A and x as an element of D. But then this specifically says A union C, and we have a C. So So I think we're getting tricked by our selection of x. It's possible that we're getting tricked by our selection of x here. So D, where we introduce this quantifier, D is an element of the set containing these elements y such that y equals the set containing, no, such that y is equal to A union C. Okay, and C is an element of B. Hmm. Well, I think actually this would have been a mistake anyway, right? And the hint that this was a mistake, getting a handle on what kind of mistake this was is difficult, but the hint that this is a mistake is that we inserted this. Okay, so instead, if and only if x is an element of A, or for all C, if C is an element of B, then x is an element of C. Okay. If and only if. that's how we arrive at our tau expression. Interesting. Tau of C is equal to A union C. The big intersection of the tau of C, where C is an element of B. Colon here instead of semicolon. Okay. Okay, that's not all we require for this definition. Ah, I see. So then we say assumption if. Okay, let's write it out. Assumption. There exists a C such that C is an element of B. Okay. Hypothesis. Okay. Which is a way of saying there exists a C such that C is an element of B, then, which is what the theorem was telling us, then with the lightest blue instead of true blue. Indicate that. Then X is an element of A union B. No, A union big intersection B. That's not a big intersection. That's a small intersection. Okay. And there exists a C such that C is an element of B. Actually exists a D such that whatever. Let's see. Yeah, actually we can do that. If and only if for all C, C is an element of B, then X is an element of A union C. And ran out of room, but that's okay. Yeah, what do we do with that? So C is an element of B. This mysterious text filled with mysteries. I don't think math books are supposed to be mysterious. Yeah, I can't figure out how we're supposed to incorporate this. Well, so this blue statement is saying that there exists. Okay, so if we say um, for all C, C is an element of B, then X is an element of A union C. Okay, and there exists a D such that D is an element of B. Okay. Well, then we can seemingly step down. Well, and we can and on. So what we'd want to do here is say and X is an element of A union D. There exists a D such that D is an element of B and X is an element of A union D. Okay, why do I care about that? Because that's part of the definition of the big intersection of the tau of X. One wonders if thinking about the point of tau, the point of the tau definition would tell us something, would give us a hint as to how it works. Not gonna try it. I'm not interested in thinking about the meaning of these symbols. I am interested in learning how to manipulate the symbols. Let me see. Okay, for some reason, this definition that I've written down is not facilitating this. I keep looking back at this definition I've written down, and it is not helping me. Right, so the big intersection of tau of X such that X is an element of A is equal to the big intersection of the set containing its elements Y such that there exists an X such that Y equals the tau of X and X is an element of A. Okay. X is an element, rather, S is an element of the big intersection of the tau of X such that X is an element of A if and only if for all C, if C is an element of the set containing its elements if and only if C is equal to tau of x and x is an element of A, then S is an element of C. Okay. If and only if. Okay, so now we want to take this expression there exists an set containing these elements y such that there exists an x such that notably so we want to sub out tau of x. Which in this case, as we've observed, yeah, this remains difficult, strange. As we've observed, this tau of x substitution is supposed to be, let's see, in this case, A union C, so it's the big intersection of A union C such that C is an element of B. Okay. Tau of C is equal to A union C. Okay. So it's going to be for all D. Okay. There exists a C such that I don't get it. Let's see. There exists a C such that D is equal to A union C. And C is an element of B. Then, say S is an element of D. just gonna go with T instead of S. S is not sufficiently distinct. T is an element of D. Okay. So this might actually be the statement that D is equal to the empty set. For all D, not D is an element of B. Then we could have that T is an element of A union D. This would be false. And then we would have, and there exists a C such that C is an element of B. I don't know how that's supposed to get us to saying that. Don't know how that's supposed to get us to saying that the big X is an element of the big intersection of A union C such that C is an element of B. Well, it would literally be if and only if there exists a C such that C is an element of B and T is an element of A union D. Unclear. Alright. Need time for calculus. Confusing as ever. Let's see. Did I drop the color pencil at the side to make it look more aesthetic, which you believe is working? No. Though, that is a good point, yes. It does look good on the camera, doesn't it? But no, we use the colored pencils extensively. They're not for decoration. Though they do decorate. Anyway, that was set theory, axiomatic set theory. A confusing subject, not for the faint of heart. Okay, now. Well, this isn't such an impressive page. Hold on. I'll put an impressive calculus page from my notebook on camera, and it'll trick people into thinking that that's what we're going to be using. calculus shortly. Be back soon. Incidentally, what subject does it remind you of? Well, I'm back. I'm going to get the blood pumping before I do calculus. Consequently, here, watch me do exercise. I try to weave in exercise segments 10 minutes at a time. Axiomatic set theory is a kind of algebra. It might have reminded you of a kind of algebra. Oh, I need a timer. One moment. It's an extension of logic, but then logic is itself an algebra, as I've been told. I've not yet gotten into abstract algebra, but we'll do that eventually. After linear algebra, which comes after calculus. We're still failing to juggle quantifiers effectively. Our there exists and for alls are not consistent. I mean, the puzzle we were working on today was effectively how do you translate the definition of the big intersection for the tau operator into a particular instance. So the tau operator is an abstraction of an operator. Tau is a stand-in for any operator like intersection or union. Well, it's like a stand-in for an operation so far. I mean, we've had tau of x is equal to, e.g., the set containing x union the set containing 4 was the object example the author gave. Okay, so now when I say tau of x, I mean that I make a set out of x and 4. I put x and 4 in a set together. So when I say the big intersection of A union C such that C is an element of B, instead of the big intersection of tau of x such that x is an element of A, then B is a stand-in for A, C is a stand-in for x. So we're really saying tau of C is equal to A union C. Or really A union anything. A union into a set. And then, right, well, it's just a game of substitution, but then the game gets complicated. I couldn't figure out how to sub in all of the expressions for our definition of the big intersection of tau of x, such that x is an element of A. Kept getting mixed up. I guess I'll have to try harder. I need to run my phone out of electricity, out of juice. It's malfunctioning. 10 minutes of squats. Yeah, that's what I'm feeling. Camera's kind of off, slanted. Oh. Two more minutes. Actually, let's do this activity. Weave this in. Yeah, I mean, 10 minutes is an interruption, to be sure. It's like you do 10 minutes of exercise and people are gonna think, what are we doing? What happened to the mathematics? Why aren't we doing math? I know, we'll be back to doing more math shortly. Just 10 more seconds, and the math will continue shortly. Okay. All right, that's enough of me. Look at the table. But the table's upside down. I don't want to look at an upside down table. Let's see. There you go. All right, now. Hello, I responded. Hold on one moment. Not fast enough, apparently. Oh well. Alright, now calculus. What about it? Exponential and logarithmic functions. Let's give this another go, shall we? All right. We ostensibly started this section yesterday, or whenever we did, but I kind of got distracted by my hair. Okay. Learning objectives. Identify the form of an exponential function. Explain the difference between the graphs of x to the b and b to the x. Recognize the significance of the number e. Identify the form of a logarithmic function. Explain the relationship between exponential and logarithmic functions. Describe how to calculate a logarithm to a different base. And identify the hyperbolic functions, their graphs, and basic identities. Alright. In this section, we examine exponential and logarithmic functions. We use the properties of these functions to solve equations involving exponential or logarithmic terms, and we study the meaning and importance of the number e. We also define hyperbolic and inverse hyperbolic functions, which involve combinations of exponential and logarithmic functions. Note that we present alternative definitions of exponential and logarithmic function in the chapter Applications of Integrations and Proof. Okay, sure. Exponential functions arise in many applications. One common example is population growth. For example, if a population starts with p sub 0 individuals and then grows at an annual rate of 2%, its population after 1 year is p of 1 equals p sub 0 plus 0.02 times p sub 0. Makes sense. That's our 2% growth. And then we factor out the p sub 0. We get p sub 0 times 1 plus 0.02. And then p sub 0 times 1.02. Now again, this is a little bit confusing, but on the other hand, it's a little bit confusing that we have p sub 0 times 1.02 and then we have p of 2. We typically have our constant values out front, but what this actually is a continuation of this expression. We factored out the p sub 0, so now this is a variable outside of the parens. And then we have that constant value in the same position as it was in before. Alright, and then we are immediately following this up with p of 2, which is not p times 2, unlike this term. P of 2 is equal to p of 1 plus 0.02 times p of 1. Alright, which is once again our 2% growth rate. And we have this 1.02 again, and then we have p sub 0 times 1.02 squared. Alright. In general, its population after t years is p of t equals p sub 0 times 1.02 to the t, which is an exponential function. More generally, any function of the form f of x equals b to the x, where b is greater than 0 and b is not equal to 1, is an exponential function with base b and exponent x. Alright, let me turn on my highlighting. There we go. Any function of the form f of x equals b to the x, where b is greater than 0 and b is not equal to 1, is an exponential function with base b and exponent x. Okay. Exponential functions have constant bases and variable exponents. Alright. Note that a function of the form f of x equals x to the b for some constant b is not an exponential function, but a power function, x to the b instead of b to the x. To see the difference between an exponential function and a power function, we compare the functions y equals x squared and y equals 2 to the x in table 1.10. We see that both 2 to the x and x squared approach infinity as x tends towards infinity. Eventually, however, 2 to the x becomes larger than x squared and grows more rapidly as x tends towards infinity. In the opposite direction, as x tends towards negative infinity, x squared tends towards infinity, whereas 2 to the x tends towards 0, and not, notably, negative infinity. The line y equals 0 is a horizontal asymptote for 2 to the x. Here's our graph, where we can clearly see diminishing to 0, whereas x squared launches off to infinity. Alright. Additionally, we have our table of values. Okay. Evaluating exponential functions. Recall the properties of exponents. If x is a positive integer, we define b to the x to be equal to b times dot 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 times b with x factors of b. If x is a negative integer, then x equals negative y for some positive integer y. Yeah, I'm not sure. Well, okay. And we define b to the x equals b to the negative y equals 1 over b to the y. What is this? What work is that doing, I wonder? What do I mean? If x is a negative integer, then x equals negative y for some positive integer y, and we define b to the x equals b to the negative y equals 1 divided by b to the y. Okay. Also, b to the 0 is defined to be 1. Right, so I guess this is giving us the option of removing the negation in this 1 over b to the y expression. If x is a rational number, then x equals p divided by q, where p and q are integers, and b to the x equals b to the p divided by q equals the cth root of b to the p. For example, 9 to the 3 halves equals the square root of 9 cubed equals 27. However, how is b to the x defined if x is an irrational number? For example, what do we mean by 2 to the root 2? This is too complex a question for us to answer fully right now. However, we can make an approximation. In table 1.11, we list some rational numbers approaching root 2, and the values of 2 to the x for each rational number x are presented as well. Okay. We claim that if we choose rational numbers x getting closer and closer to root 2, the values of 2 to the x get closer and closer to some number L. We define that number L to be 2 to the root 2. Okay. Well, and notably, these are all rational values. So if nothing else, we could have this as 1414213 divided by 1000000. I'm not sure if I said the correct number of zeros, but it doesn't really matter for this case. Alright, or it doesn't really matter. Alright, so bacterial growth. Well, okay, we could figure that out. If we had 14 divided by 10, 141 divided by 100, by 1,000, 10,000, 100,000, which is 6, 1 million, which is 7. Is that right? 14 divided by 10. Okay. Okay, so 7 zeros. No. 6 zeros. 1 million has 6 zeros. Why would... Okay, never mind. 5 zeros for this one. Alright, bacterial growth. Suppose a particular population of bacteria is known to double in size every 4 hours. If a culture starts with 1,000 bacteria, the number of bacteria after 4 hours is n of 4 equals 1,000 times 2. Okay. The number of bacteria after 8 hours is n of 8 equals n of 4 times 2 equals 1,000 times 2 squared. In general, the number of bacteria after 4m hours is equal to... Rather, the number of bacteria after 4m hours is n of 4m equals 1,000 times 2 to the m. Okay, letting t equal 4m, we see that the number of bacteria after t hours is n of t equals 1,000 times 2 to the t divided by 4. Alright, let's try to parse this sentence because I don't really see what this is saying. Suppose a particular population of bacteria is known to double in size every 4 hours. If a culture starts with 1,000 bacteria, so it doubles in size every 4 hours. Okay, hence this 4m hours. If m is 1, for instance, then we would have 4, and that would be the doubling period. Okay. And since we are, let's see. Yeah, so what we're currently trying to figure out is how does this sentence justify writing out this formula? Okay. How do we explain that to ourselves? The number of bacteria after 8 hours is n of 8 equals n of 4 times 2 equals 1000 times 2 squared. Okay. Well, and so number of bacteria after 8 hours is n of 8. Okay, that's twice what n of 4 was because the doubling period is 4 hours. So one point here is that this 4 to 8 is not due to a doubling of hours. Which is a confusing point. The pattern that you might get out of this is 4 to 8, and then the next one would be 16, but actually the next one would be 12. Because the doubling period is 4, we would be putting 2 to the 3 here for 12, as opposed to putting it up there for 16. Okay. In general, the number of bacteria after 4m hours is n of 4m equals 1000 times 2 to the m. Okay, so where are we getting this m from? What does that mean? So 4m hours. Well, so and in this sequence it would be 1, 2, and then 12 would be 3m, where m is 4. No. Rather, where we have a constant multiplier 4 on m, so we would have 4 times 1, 4 times 2, 4 times 3. In general, the number of bacteria after 4m hours is n of 4m equals 1000 times 2 to the m. Okay, so this would be, well, and so if we had 4 times 1, this would be 2 to the 1, 4 times 2 is 8, 2 to the 2, 4 times 3, 2 to the 3. Alright. Letting t equal 4m, we see that the number of bacteria after t hours is n of t equals 1000 times 2 to the t divided by 4. Alright, so we just take our doubling period and we say m effectively means the number of doubling periods, which is not doubling the number of hours, again, but doubling the population, which happens after 4 hours. Alright, so find the number of bacteria after 6 hours, 10 hours, and 24 hours. Very well. And now we have the challenge. Our old calculus notebook was filled with color and insights. Can we continue to find insights and opportunities to color? I don't know. Alright, let's find out. 1000. Let's see here. So, n of t is equal to 1000 to the t divided by 4. Okay, so now we will have n of 6 is equal to 1000 to the 6 divided by 4. Okay. Now, ideally what we could do is take the 4th root. That would not be 10, though. Yeah. Because 10... 10 times 10 times 10 times 10 would be equal to 100, 1000, 10,000. Okay. Yeah, that's a shame because that would much simplify this. Yeah, I don't really know what 1000 to the 6th is. Does this turn out to be an even, not an even number, but a nice number? Let's see. .24. No, not what I meant. Let's see. No, that does not end up being a nice number. I'm not going to calculate that. Okay. N of 10 is equal to 1000 to the 10 divided by 4, which will also not turn out to be a nice number, I am assuming here. No, actually, that does... No, hold on, I forgot my parents. 1000 to the 10 divided by 4. Nope, that's also not a nice number. Actually, what is that number? Uh-huh. Well, yeah, because you could, if you can simplify down, I see. So 6 divided by 4 is 3 halves. Oh yeah, but that once again does not, no. It would be root 1000 to the 3rd. And this would be root 1000 to the 5th. Okay, and then we have 24. Six, 12, 18, 24. Okay, is equal to... And well, we could also do root 1000 to the 12th, but okay. Yeah, actually, we'll do that, sure. Which is equal to... a nice reminder here that falls out of this pattern that if I have root 1000 to the 12, I have 1000 to the 6th. They're multiplied together. All right. I did this wrong. Yep. Yep. Okay. So rather, n of t is equal to 1000 times 2 to the t divided by 4. Okay. So that n of 6 is equal to 1000 times 2 to the 6 divided by 4. Okay. Which is equal to 1000 cubed, or rather 2 cubed is, okay, we'll say 1000 times 2 to the 3 halves. Alright, so now that is 8 divided by 2, 4, 2, 4, 8, 16. 16,000. Incorrect. Why is that incorrect? 2, 4, 8... It'd be root 8, which is 2 root 2. Right. Equals 1000 times 2 root 2. Okay, now we're going to have n of 10 again is equal to 1000 times 2 to the 10 divided by 4, which is equal to 1,000 times 2 to the 5 halves. Okay, 2, 4, 8, 16, 32, root 32. Which we can divide out of 4. 4 root 2 equals 1,000 times 4 root 2. Yes. Alright, and then n of 24 is equal to 1,000 times 2 to the 24 divided by 4. Is equal to 1,000 times 2, and again we could do 12 to the 12 divided by 2, but that's equal to 1,000 times 2 to the 6, 2, 4, 8, 16, 32, 64 is equal to 1,000 times 64, which is infinity. Alright, now we move on to next page. Okay, let's see. Something popped up on my computer. Alright, let's see. Given the exponential function f of x equals 100 times 3 to the x divided by 2, evaluate f of 4 and f of 10. Alright. F of x is equal to 100 times 3 to the x divided by 2. F of 4 is equal to 100 times 3 to the 4 divided by 2, which is equal to 900. Well, it's equal to 100 times 3 squared, which is equal to 900. Alright, and f of 10 is equal to 100 times 3 to the 10 divided by 2, which is equal to 100 times 3 to the 5th, which is equal to 3, 9, 27, 81, 263. Alright. 26,000. Yeah. 300. Alright. And the reason I didn't auto-simplify is because I didn't auto-simplify in the first case. I wanted to keep the same formatting. Alright, given... did that. Alright, now... graphing exponential functions. For any base b greater than 0 and b not equal 1, the exponential function f of x equals b to the x. Hold on one moment. Oh, there it is. For any base b greater than 0, b not equal to 1, the exponential function f of x equals b to the x is defined for all real numbers x and b to the x greater than 0. Okay. So this is saying, and this is a kind of phrasing that we're having to get, that we have to get used to. And I guess this is why calculus is considered this kind of bridge course towards advanced mathematics, because this kind of phrasing, we get to parse this kind of phrasing in a simplified environment relative to more abstract mathematics. So for any base b greater than 0 and b is not equal to 1, so base b over here, the exponential function f of x equals b to the x is defined for all real numbers x. So it doesn't matter if you choose negative or positive, and b to the x is greater than 0. Every output is positive. Therefore, the domain of f of x equals b to the x is negative infinity to infinity, and the range is 0 to infinity. To graph b to the x, we note that for b greater than 1, b to the x is increasing on negative infinity to infinity. For a base that is greater than 1, the function is increasing on negative infinity to infinity. And b to the x tends towards infinity as x tends towards infinity, which gives us a rough sketch of our function here. Whereas b to the x tends towards 0 as x tends towards negative infinity. On the other hand, if 0 is less than b is less than 1, f of x equals b to the x is decreasing on negative infinity to infinity. And b to the x tends towards 0 as x tends towards infinity, whereas b to the x tends towards infinity as x tends towards negative infinity. Okay. Because we're inverting. Because to have a negative exponent means to invert the... Right, so if x is negative here, we're inverting our 1/4 and then raising it to some power. Okay. Fair enough. Where again, the point of learning this is not because we're interested in exponentials per se, but because we're interested in analysis, in taking functions and talking about them. So I think... Alright, note that exponential functions satisfy the general laws of exponents. To remind you of these laws, we state them as rules. Okay. Laws of exponents. For any constants a greater than 0, b greater than 0, and for all x and y, b to the x times b to the y equals b to the x plus y. Okay, we add them. If I divide, I subtract them. B to the x to the y, you multiply the exponents together. If I have a times b to the x, a to the x times b to the x, and if I instead divide a and b, a to the x by b to the x, we have a divided by b to the x. Okay. Using the laws of exponents. Use the laws of exponents to simplify each of the following expressions. Ah, good old calculation. Why isn't all of math just doing calculation? Let's see. So 2 times x to the 2/3. Cubed. Divided by 4x to the negative 1/3 squared. Alright, so now we multiply. Okay. When we have exponents set up like this. Okay, so this is equal to, well, yeah, 2 cubed times x to the 2/3 times 3. Divided by 4 squared times x to the negative 1/3 times 2. Okay. Which is equal to 248, which is x. So one point here is that, how do I phrase this? This rule that we multiply 3 rather, that we multiply this exponent here by this exponent. Yeah, that gives me a substitution rule. It gives me a rule for what to do on the other side of the equality symbol. I multiply in this fashion. The rules that we've been given are rules for filling in equalities, if nothing else. Alright. 8x squared divided by 16x to the negative 2/3. Okay. So this negation is a flip command. Okay. So we will have 8x squared times x to the 2/3. That was just a bad parent, I think. Alright. Divided by 16. Okay, and actually that divides out. So we have x squared. So now we are going to... Let's check our rules again. We're going to add our exponents, if I recall correctly here. Yeah, x plus y. So actually we could have... Alright, let's finish this calculation. I'll do it in a different way. Well, actually, we have another exercise next. We can do it there. Yeah, alright, so we're going to have this we add. So this is going to be 6/3, x to the 6/3, so 8/3. X to the 8/3 divided by 2. Okay. Actually, yeah, let's just do this again. So we have 2x to the 2/3 divided by 3, cubed, divided by 4x to the negative 1/3 squared. Alright, so now what rule do we want to apply? I want to apply... I want to separate these out. Alright, so we're going to have a times b to the x equals a to the x times b to the x. Alright, so this is equal to 2 to the 3. Okay, and this is x to the 2/3 to the 3. And then this is 4 to the 3 times x to the negative 1/3 squared. Alright. Now what rule do I want to apply? I would like to apply the rule where we, b to the x to the y is equal to b to the xy. Okay. So now this is going to be, we can calculate this out, 8 times x to the 3 times 2 divided by 3. Again, this is a substitution rule, a typographical rule, as it were. Okay, and then we're going to have, this should have been 2, not 3. So this is going to be 16 times, now x to the 2 times negative 1/3. Alright, and now this is not rule-based, this is merely Calculative, sure. 8x squared divided by 16x to the negative 2/3. And I don't know, I'm recurringly astonished by this observation. When I was originally learning this, I think I would have been stuck with the idea that when I was learning this decades ago now, I would have been stuck with the idea that, like, you should be able to derive this fact. Alright, like, as if this is a point of logic, as it were. I wouldn't have phrased it in that term, but, like, not that this is merely a rule that we've established, but that you should be able to figure this out, but you can't figure this out. This isn't figure-outable. Someone has to tell you that this is how exponents work. Anyway, now what rule do I want to apply? Let's see. So we don't have a common base here. We can divide out this so that we get x squared divided by x 2x negative 2/3. Okay. Then what? Now, so our next rule that we want to invoke, though it's not one of the rules we just... Oh, what camera am I on, by the way? Okay, we're on the right camera. The next rule we want is that b to the negative y is equal to 1 over b to the y, which is to say, oh, and then 1 over b to the negative y is equal to 1 divided by 1 divided by b to the y, which we can also phrase as 1 divided by 1 divided by 1 divided by b to the y, which is equal to b to the y. Okay, so I want to say we have x squared times, we can do 1/2 x squared times x to the negative 2/3. We could do, that wouldn't be right, no. It would rather be 1 divided by x to the negative 2/3. Okay, which is equal to 1/2 x squared times x to the 2/3. Okay, and now I have the same bases here, notably. And I want to apply the rule. So if we wanted... All right. And now we apply the rule that we add these exponents. So, yes, let's see. B to the x times b to the y is equal to b to the x plus y. And that's the last step, so I'll just put that over here. So again, this is 6/3, 8/3. 1/2 x to the 8 divided by 3. Okay. Now, same idea. All right. We have x cubed y to the negative 1 squared divided by x squared. No, rather x times y squared to the negative 2. Okay. Anybody in chat? Hello, St. Just Germany. Nope, you're gone. Alright. Not interesting enough of content. Shame. Alright, now, what do we want to do first? I would like to invoke the rule according to which, let's see. See. B to the negative y is equal to 1 divided by b to the y. Alright. So I will say that this is equal to x cubed y to the negative 1 squared times x y squared. Alright, now I would like to invoke the rule that b to the x. No, we need to distribute, I suppose. Alright, ab to the x. Hold on, I'm going to do this here so I can keep a column. Alright. ab to the x is equal to a to the x times b to the x. Alright, so some coloring scheme here. That. From which we will obtain that x to the 2 times 3 times y to the negative 1. Nope. 2 times negative 1. Okay. And then we will have x to the 1 times, nope, 2 times 1. 2 times 1, y to the 2 times 2. Okay. And now I would like to apply the rule that, let's see. well, I'm just going to do another equality here because I want to simplify. So this is equal to x to the 6th times y to the negative 2 times x squared times y to the 4th. Alright. Now I would like to invoke the rule that well, okay, so we could note here, yeah, okay. If we really had to go normal form, go into normal form for this, we could observe that this is x to the 6th times x squared times y to the negative 2 times y to the 4th. Alright, now I would like to invoke the rule that b to the x times b to the y is equal to b to the x plus y. Alright. And the formatting here, okay, so Spanish orange. And now we will say x to the 6 plus 2 times y to the negative 2 plus 4, which is in turn equal to x to the 8th times y squared. Alright. Proved. Alright. Yeah, and yeah. Alright. Use the laws of exponents. The laws of exponents. To simplify, 6 to the negative 3rd times y squared. 6x to the negative 3rd, that would have been strange. 6x to the negative 3rd times y squared divided by 12. Times x to the negative 4th times y to the 5th. Alright. I'd like to take a simplification step, get those 6 and 12 out of there, which we are perfectly free to do. Nothing's stopping us from doing that. Alright, which is equal to x to the negative 3. Oh, we have exponents on these? No, actually. Okay. X to the negative 3rd times y squared divided by 2. X to the negative 4th times y to the 5th, which is in turn equal to 2 times x to the negative 3rd times, no, hold on, we're not going to have enough room. Okay, so instead we're going to say this is equal to 2, oh, so no, we need to invoke a rule here, and the rule, which is not actually one of the laws, it's that we were just given once again, but we are going to invoke the rule that, let's see, b to the negative y is equal to 1 divided by b to the y, semicolon to clarify here. 1 over b to the negative y is equal to b to the y. And I'll just do a little bit of underlining there, that's proven. Okay, and then we're going to say 2 times x to the negative 3 times y squared times x to the 4 times y to the 5th, y to the negative 5th. Okay. which is in turn equal to 2 times x to the negative 3 times x to the 4th times y squared times y to the negative 5th. And now I would like to invoke our rule that adding exponents. All right, what is that rule exactly again? We get b to the x times b to the y is equal to b to the x plus y. All right, so then we will be saying 2 times, I have a colon here, 2 times, we add this up, x to the 1 times y to the negative 3. Okay, which is equal to 2x divided by y cubed. All right. And now if I want the coloring scheme, rule here, application, rule here, and application. Oh, well, I guess we should have reapplied the rule. B to the x times b to the y is equal to b to the x plus y. Alright, and then we'll get Spanish orange over here. Alright. I believe it. All right. The number E. That's not a number, that's a letter. Oh, what time is it? I got about 10 minutes. Okay. I've not had much of my spicy beverage. Alright, what about E? What is this? What is this strange letter number? A special type of exponential function appears frequently in real-world applications. To describe it, consider the following example of exponential growth, which arises from compounding interest in a savings account. I thought you said real-world applications. Suppose a person invests P dollars in a savings account with an annual interest rate R compounded annually. The amount of money after 1 year is A of 1 equals P plus RP equals P times 1 plus R. Yeah, okay. The amount of money after 2 years equals, so this is the same pattern that we had before. Our rate, which was before 2%, so 0.02, is now just R. Okay. The amount of money after 2 years is A of 2 equals A of 1 plus R times A of 1 equals P of 1 plus R times P of 1 plus R equals P. Rather, we got confused again, yeah. A of 2 equals A of 1 plus R times A of 1. And we perform some substitution here. Okay, then we have P of 1 plus R of R. No. P times 1 plus R plus R. Oh, I'm confused again. A of 1 equals P plus R times P, which is equal to P times 1 plus R. Okay. Is my algebra going wonky? This doesn't seem to add up. P of 1 plus r times p. It's not p. This convention is horrible, but it's p times, right? Because we have p, which is principal. We have principal plus r times principal equals principal times 1 plus r. So when we say a of 1, we perform this substitution. We get p times 1 plus r plus r times p times Yeah, r times p times 1 plus r, because, yeah, so, I mean, actually what we could do here is write this out and use color to differentiate. Oh, an excuse to use color. Huh. Alright, let me see here. So we're gonna have a of 1. Alright, this is a tau operator, you might say. Or, well, you might say it's an operator. Okay, a of 1 is equal to p plus rp is equal to p times 1 plus r. Alright, now what am I thinking? I'm thinking we should designate a color for constants. Constants. That's a good name. We should designate a color for constants. Alright? P is a constant, R is a constant. Okay. 1 is not a constant. I'm not really sure what I would name 1 if we're using the word constant for these. What color do I want to use for constants? Well, I think we use this for variables. Tuscan red. That makes good sense. Yeah, we don't have a good color for this. Well, we could use the brown range for differentiating variables, constants, maybe inputs. Okay, so then I will use sienna brown, maybe. Okay, and then we can have a distinction between a letter constant, because we want to be able to show, we want to be able to observe that this 1 is not the same as this one, for instance. So literal integer could get dark brown. Alright, so this is a constant, 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 constant. Okay, and then this is a literal integer. Alright, and I'll put a key here. Tau. Or operator. Okay, and then we will have this color, which is a constant. Alright, and then we will have this color, which is literal constant. I'll just say literal. Alright. Now what is the point? So when we say a of 2, oh, and then we need a color for this. Does this differentiate enough? Is that different enough? Maybe not. Then we might not have enough. Well, brown just doesn't differentiate so well on camera. I mean, Tuscan red is different enough. But I don't know, this is kind of a golden brown, kind of. So I think it might be different enough. Alright. Oh, yeah, surely that's different enough. And that's an input. Maybe there's a different word for that. Operand, you might say. / argument. Which does not really mean the same thing as operand, but we'll use that for now. Okay, so then we have the next expression, which is that a of 2 is equal to a of 1 plus r times a of 1. Alright. And now I guess we could do underline this, because equality is also an operator, I think. We should think of it. Maybe we should think about it that way. But no, I'll just forego. Alright, so there we have an argument, argument, and argument. Okay, we have an operator, operator, and an operator. Okay, and then we have r, which is a constant. Alright, and now we have equal to p of 1 plus r plus r times p of 1 plus r. Okay. Now, so we have a constant. We have another constant. We have another constant, and then another constant, and then another constant. We have a literal here, and a literal here. Alright. Which is equal to p times 1 plus r squared, where this is a literal, and this is a constant, and this is also a constant. And this equation appears to be incorrect. Why does it appear to be incorrect? Well, where is this? What am I not getting about this? Hold on. Well, so we have, if I factor out, I say p times 1 plus r times, I see. I was confused, but this maybe helped clarify it, maybe it didn't, I don't know. Times 1 plus r. Okay, which is in turn equal to p times 1 plus r squared. Alright. Oh, we're over time. Alright. Well, we'll get back to this tomorrow. Okay. See you soon. Have a good one. Until we meet again. Etc.